Systems of equations are problems in which you have two equations, or possibly more, and you have two or more variables as well, and you're trying to solve for the variables. So in order to solve for a certain amount of variables, you need that many equations. So if you have two variables that you want to solve for, you need to have two equations. So there's two main ways of doing this. There's by what's called combination or by substitution. So let's just assume, first of all, that we have a linear system of equations. So for example, if you had something like 3x plus 2y equals 5, excuse me, and if you had something like 4x minus y equals 3. So if you just had one of these equations, you definitely could not solve for x and y because you wouldn't be able to isolate it. But since you have two, it's definitely possible that you could isolate one of the variables and solve for both. So I'm going to do this by both methods, the combination and the substitution. So by combination, what you want to do is add the two equations together, but in doing so you want to cancel out one of the variables. So if you notice here we have a 2y. If we made this a negative 2y, in other words, multiply this whole equation by 2, then if we put these together we'd get 2y minus 2y and it would cancel out. That's what we want to do. So we would add 3x and 8x, so that would be 11x. 2y and negative 2y would cancel out, and 5 plus 6 would be 11. We get 11x equals 11. You can see here that means x is 1. And then by plugging it back in to either of the equations, it's important that you can do it in whichever one, you can solve for y. So you can see here if we plug this back in for x here, we'd just get 3 plus 2y equals 5. And you could obviously solve that equation for y. So that's combination, and that's a good thing to do if your equation, if you have both linear functions like this, just x and y, and no powers of x and y, and your coefficients are all just regular integers. It's usually easy to do that. So substitution, the other method, is where you solve for one variable and plug it into the other equation. So for example, let's take this equation, but I'm going to rewrite it as 4x equals 3 plus y by adding y over to the other side. And then I'll subtract 3 to isolate y. So this here, 4x minus 3 equals y, is the same thing as this equation, but now that it's just y equals, instead of the y here, I can write all of this, and now we'll only have it in terms of x. So by plugging this in, so substitution, so we would get 3x plus 2 times, now instead of y, we're going to write all of this stuff, 4x minus 3 equals 5. You can see now you only have one variable, so you can clearly solve for x. So this would be 3x plus 8x minus 6 equals 5. 11x equals 11, which again gives you x equals 1, and then you would plug it back in. Here would be the easiest case there to get y also. So that's using combination and substitution to solve a system of equations. Now there's a couple special cases. It's very possible that you get a system of equations that looks something like this. So instead of trying to do our methods, let's look at this first and see what this is really saying. X plus y equals 1, 2x plus 2y equals 2. If you notice, this second equation is just a multiple of the first one. We just multiply everything by 2 and you get the second one. So what that means is these two are actually the same thing, and therefore you would not be able to solve for this. So this is what we would say this has infinitely many solutions, because anything that could work in one will work in the other. There's no specific set of answers. So whenever you see that one is just a multiple of another, you have the same line, and it works out for infinitely many solutions. Another one you might come across is something like this. What you want to notice there is if you tried our combination method by just subtracting the second equation and canceling everything out, you get a nonsensical statement at the end. You get 0 equals -2, which is just not true, and you don't even have an x's and y's left. This is what we have so both of these are lines, remember, and solving these is essentially finding their intersection. This is when you have a situation where if you were to graph this, it would look like this. You have parallel lines that never cross. So if you do your work and you get down to this and that doesn't make any sense, that means you have no intersection. There's no solution. So here you have infinitely many solutions. Here you have 0 solutions. And most of the time in a linear system, you're going to have one solution. So the last thing I want to point out is how to do systems of equations if you don't have linear equations. It's not really any different, except that you won't be able to use the combination method. So, for example, if you had the equation y equals x squared, and the line y equals x plus 1. You can see here, since x squared and x now are completely different things, you wouldn't be able to use a combination method to eliminate anything. You have to use substitution. So you would just plug in x plus 1 instead of y in this equation. It would now be all in terms of x, and you have to solve it. It'd be a quadratic equation. So this is oftentimes what you're going to have if you have to think about systems of equations where one of them is a circle or one of them is a line. In that case, if you have anything other than linear equations in your system, you have to use the substitution method. But that's the 3 different types you get for linear and just an approach for the nonlinear systems of equations.